For inviting me. It's a great pleasure and honor to be here celebrating Alex. Before I get to the actual talk, I have something else here. The first novel by James Joyce had the title, The Portrait of the Artist as a Young Man. Forget the novel, but we can paraphrase the title, Portrait of the Mathematician as a Young Man. So this picture was also taken at the 70th birthday celebration, the one for Fred Gehring in Michigan in 1995. The other people in the front row are all here, and Alex seems to be in a good mood. When I went through all pictures, the only other older picture I was able to find was from 3 years later, 1998. I believe it was in late May, taken in the common room of University College London, presumably before or after somebody's talk. The third person is Boris Korenblum, who is no longer with us. Then something more recent here. When the email came from the organizers that Alex wouldn't be here, my wife and I called Alex and asked if we could visit him, and he said that would be fine. So he also agreed that I could show here some of these photos taken in West Lafayette on the 15th of June. The one on the left taken in Alex's apartment. He has a beautiful view over a nature reserve which is nearby. To be able to walk there, one has to drive maybe a mile. Alex seemed to be quite strong and in a good mood, and so he took us there. It's next to a pond called Celery Bog, and so the photo on the right is taken there. He took us for a long walk through the forest, but before you turn and get to the forest path, there is a paved path. And I hope that in some symbolic sense, there would also be a path to better days for Alex after his treatments, hopefully successful. So thank you, Alex, for that day and all the best for the treatments. So I should now get to the talk, and the next slide is the outline of the talk. But before I get to that, I'd like to make some general comments just to say very briefly what's essential about the talk. So moments are certain numbers associated with measures in the ordinary sense. I will call them positive or non-negative interchangeably, meaning the same thing. And in the classical theory of moments that really goes back to the mid-19th century, the question is what can be said about these moments, what kind of real numbers could be described so that they would be the moments of some positive measure. And if so, then under what circumstances would this measure be unique? So I noticed that one can actually, so to say, go in the opposite direction and begin with the signed measure. And then one can prove that under suitable assumptions on the moment and absolute moment of the signed measure, one can show that the signed measure actually is a non-negative measure. This can be done on many sets. I think the real axis is the most interesting one, so let's think about that. So on the real axis, the signed measure could be of the form f of x dx for some function f. Then if one gets the conclusion, that means f is non-negative almost everywhere. And in all applications, I can think of that all functions are continuous, and in that case, the conclusion would be that the function is non-negative everywhere on the real axis. Polynomials don't have finite moments, but by a little trick, one can apply the results to them also. So one gets criteria in terms of moments, if and only if criteria for a polynomial to be non-negative on the real axis. And one can apply this to polynomials in any finite number of real variables as well. And then there are some further applications of this nature. So here's the outline. First, I will recall the definitions of moments and absolute moments. The classical theory of moments is very broad. I won't be able to review anything other than what we really need here. And then come the new results, uniqueness criteria for signed measures. I think that's really the basic thing from which all the other things can be deduced. Uniqueness criteria for real and complex functions, positivity criteria for signed measures, and as a result of that, positivity criteria for functions and polynomials. The next thing may not turn out to be of any great interest, but examples of positive polynomials. They might be positive for trivial reasons. And then there are all results to the effect that something is true if some polynomials are positive or non-negative on the real axis. and therefore one can also get criteria for polynomials and certain entire functions to have only real zeros. And lastly, I noticed that there's a certain relation to so-called polygon functions. So I will try to get through all of this. So I'll just assume that we deal with the real axis, even though similar things can be done on other sets. We'll assume that sign measures are Borel measures, and to avoid simple cases, not the zero measure and not concentrated at the origin, which means that the absolute value of the measure on the real axis minus the origin is positive. So if we have a signed measure on the real axis, then of course it has the usual Jordan decomposition, nu equals nu plus minus nu minus, where nu plus and nu minus are mutually singular non-negative measures. And as usual, the absolute value of nu is defined as nu plus nu minus. So if we have a measure in the usual sense, then of course it's equal to the positive part and the absolute value, and the negative part is zero. Well, so moments are defined so that I'll denote the moment of a signed measure by Sn nu. The Sn notation is quite standard. The integral in this case over the entire real axis of x to the n d nu x. Sorry. That far, okay. Then the absolute moment is something you get when you take every possible absolute value there. So you integrate the absolute value of x to the n with respect to this absolute value of nu measure. Assuming, of course, that these integrals exist and are finite. Well, obviously, the moment of nu is the moment of nu plus minus the moment of nu minus, which is useful in some proofs. And by the assumptions, the absolute moments are all strictly positive. For even indices, the absolute moment of nu is the same thing as the ordinary moment of the absolute value of nu, just because x to the 2n is always non-negative. And if nu is a non-negative measure, then the absolute moments with even indices are the same as the moment, which has some bearing on even the classical theory, because the absolute moments are used in some proofs, but you see them in the statements of theorems, because only absolute moments of even index are needed, and so then they are just moments. Okay, so let's go back here. All right, and then of course there's some this type of inequality. So one often wants to consider functions, so one takes the measure to be f of x dx or something. And so it may be convenient to have a notation where you just have f instead of writing f of x dx all the time. And of course, the moments and absolute moments of functions would be defined in the same way if the integrals exist and are finite. And we always assume f doesn't vanish almost everywhere, and then the absolute moments are all strictly positive. What are moment problems? So let me first mention here that even though I will later limit myself to the real axis, moment problems have been in great generality. So if we have a closed subset K of a Euclidean space and a measure mu on K, then one could just in the obvious way define moments with multi-indices where the exponents are all non-negative integers if the integrals exist. So I will be taking d to the v1, so we have a subset of just r. Then the moment problem is that if real numbers mu n are given, under what circumstances is there a non-negative measure nu such that the moment s n nu is always mu n, and if so, whether nu is unique. So that's what we mean by a moment. So these have been solved in various cases, at least the existence problem, the uniqueness is tougher. There are fairly simple answers to the uniqueness problems. So if K is all of R, one calls this the hamburger moment problem. So somebody called Hamburger actually solved it in 1921. If it's a half line, it's called a Stieltjes moment problem. Stieltjes studied it in 1885. And if we have a compact set, one might as well take it to be the interval from 0 to 1. Then it's the Hausdorff moment problem. The Hausdorff moment problem, or generally these compact problems, have the special feature that if there's a solution, it's always unique. But in the unbounded case, there's no need for that. So there was probably a long time from the 1920s until late 1970s when not too much was actually done about moment problems. In 1979, Schmugden started studying systematically this more general case of a closed subset of RD, and after that he was followed by many others. Well, I wanted to give the idea that moment problems are still being studied very actively, so here I have a reference book from 2010, and I simply copied from the introduction a very long list of all kinds of applications of generalized moment problems. It's become very computational. This book, for instance, is full of sort of explanations of how you can program a computer. There's actual code there to solve this type of problems. The generalized moment problem really is more generalized. The question is how to maximize or minimize some functional under constraints that something is true or assumed to be true about some moments. We don't need to look at this list further, but I just want to give the impression of what people have been doing. Well, let's then review classical moment theory, some simple things. So here's a simple thing that probably was noticed very early in the 19th century. If you have a non-negative measure nu on the real axis, then for all real numbers C0, C1 up to Ck, obviously we have a positive non-negative quantity here, the integral of the square of a polynomial with respect to nu. This would, of course, be equal to 0 if nu were concentrated at finitely many points, and if all of those points were to be zeros of this polynomial, then, of course, you get 0. There are all kinds of more refined results for measures that are supported on a finite set. We might as well assume that this is not the case, and so in such a case, if the C naughts, etc., are not all 0, we get a strictly positive number. Now, if you fiddle around with this a little bit, you see that this condition can be written in this form, a double sum Ci Cj, and then the moment with index I plus j, that will be non-negative. So that means that for each non-negative k, the k plus 1 by k plus 1 matrix whose ij entry is this moment with index I plus j is positive definite. Some of you might like to say positive semi-definite. I borrowed the standard terminology from the area of positive definite functions, where I guess they use the shortest term for the condition that's most common, and the most common condition considered is the one where you have greater than or equal to sign without any other restrictions. Well, this can also be considered in terms of determinants. And so if this measure is not concentrated at finitely many points, and if not all Ci vanish, as I mentioned earlier, then this integral is certainly positive. And that means that the matrix with these entries Si plus j is what is now strictly positive definite. Some of you might just say positive definite in this case. So that means that its determinant and leading principal minors are all positive. That's an equivalent condition, but the leading principal minors for matrices like that are just determinants of the same form, just smaller. So there are more refined results for measures supported on a finite set, but we don't need to worry about that. Well, there's this obvious necessary condition then, that if we are given real numbers mu n, and if there is going to be a non-negative measure nu that has these moments s and nu is always mu n, then of course it necessarily has to be the case that all of these matrices are positive definite. But that turns out to be also a sufficient condition. And so how do you construct measure? The measure, well, you use the Riesz representation theorem. So in this case, since I haven't put the list of references anywhere, I just mention references every now and then. Maybe I'll say at this point that there's the classical monograph of Shohat and Tamarkin called The Problem of Moments that appeared in 1943. It's extremely detailed and attributions, references, everything there. And it contains, for instance, a detailed proof of this theorem. It goes on to several pages when it's done very carefully. Now, I won't have time for anything more there. I just say it's the representation theorem. What about the moments of signed measures? There is very little literature on such things, but there's this very early result by Ralph Boas from 1939. Absolutely any real numbers could be the moments of signed measures. So that's true already on the half line, the interval from 0 to infinity. If you want such an example on the real axis, just take the measure to be 0 on the other half from minus infinity to 0. Of course, this signed measure can widely vary, but there is always one, usually not unique in any sense. So that would suggest that maybe you cannot say much about signed measures, but that is not true. Because if you don't take these mu n's to be arbitrary, if instead you impose conditions on them, if you impose conditions on the moments and absolute moments of signed measures, then you can get results as we are going to see. I tried very carefully to find other earlier literature on signed measures, and it seems it's of a very specialized nature. For instance, in number theory, analytic number theory, or maybe special functions, there are papers saying that, okay, these numbers are the moments of some function. This function takes both positive and negative values. So they are moments of a signed measure, but that's a very specialized result. Other than that, there's very recent work related to probability theory. You might expect there are just positive measures there, but it's a finite parameter problem. You take finitely many points on the real axis, associate the positive number like a measure with every second one, negative number with every second one, then do something with them. But again, it's not anything on general signed measures. What about uniqueness criteria? So I think the best that's known is this result due to Karleman. And it's really remarkable that at the same time Karleman developed his theory of what he called quasi-analytic classes, the monograph by Shohat and Tamarkin has a detailed proof taken, of course, from Karleman of the theorem we see here. And it's almost verbatim the same kind of thing that Karleman does for quasi-analytic classes. So he must have had the insight that he could use his ideas also in this context. So let's see what this says. So if we have the real numbers mu n, which satisfy this necessary condition for there to be any chance that the numbers mu n are the moments of a positive measure, then of course we know already from the previous result that there is at least one such positive measure, but the measure is unique if there is this additional condition that this series here must diverge, and you might think of the mu n there as being the moment S2n of this positive measure. So another way of saying this is that if you start with a positive measure, and if this series of S2n to the power -1/2n diverges, then the measure was the unique one with these moments. There's this weaker condition which I have copied for the sake of completeness, but it seems to me it doesn't get very much use. Now, maybe around 1850 or something, Markov had asked whether the function, essentially e to the -x² that appears in the normal distribution, is the only non-negative function that has the same moments. And from this, since one can calculate what the moments are, in that case, one can see that the answer is yes. As a general remark, you never have any uniqueness for anything here without some restrictions. What is the restriction here? In the case of e to the -x², the restriction is that the other function has to be non-negative. If you were to use what comes later, you would in fact see that if the restriction is weak and that this other function has to be at least, let's say, minus e to the minus absolute value of x or something similar, then we would still have uniqueness. The idea of Karleman is to sort of leave the real axis, go to the complex plane, and analyze this analytic function here that you get integrating over the real axis d nu t over z minus t. And he would look at it in both of the two half planes. So from this point onwards, unless I really state otherwise, all the results are new theorems. And really the basic thing is this uniqueness result for sign measures, because other results can be fairly easily reduced. So let's assume that nu1 and nu2 are sign measures on the real axis, and for neither one of them the zero measure or concentrated at the origin. So all the absolute moments are positive. We assume that all the absolute moments are finite as well, and that all the moments coincide. So the question of uniqueness is if all the moments coincide, under what circumstances will the sign measures be the same? And the answer is the sign measures are the same, provided that this series here diverges. This is like the Karleman condition, but now we are adding the absolute moments of even index for nu1 and nu2. In fact, if you go, this can be proved in one slide, which will be the next slide, but a little bit later, using Karleman's result. I went through Karleman's method to see if that would give something better, but it does not. And in fact, Karleman's own result gives essentially the same thing as well, but then he just, since he looks at positive measures only, he observes that the absolute moment with even index is the same as the moment. And then there's an assumption that for the two measures he has, the moments are the same. And therefore, this sum is just 2 times one of these moments. And then if you have 2 to the power minus 1 over 2, and that tends to 1, it won't affect the convergence or divergence of the series. So in that case, it's still the same thing, but it was possible to simplify the situation. All right, so the proof is already here. So we write each of the sign measures nu j as nu j plus minus nu j minus. And we observe that there's this thing for the moments that Sn nu j is Sn nu j plus minus Sn nu j minus. So since we assume that the moments are same, perhaps there should be an intermediate stage here, but we would get that Sn nu1 plus Sn nu2 minus is equal to Sn nu2 plus Sn nu1 minus, and then you can write that again in this form. And so we now have 2 positive measures with the same moments. So by Karleman's theorem, these 2 positive measures are the same, provided that this series here diverges. But now we just have to observe that this moment for nu1 plus nu2 minus is less than or equal to the sum of the 2 absolute moments. Therefore, if we have the assumption that was in the theorem that this series diverges, then obviously this series diverges as well, and so Karleman's result can be obtained, can be used. So there really was nothing more to that. Well, then in the same way, one can get the uniqueness result for real functions, and now we don't have to put in the assumption anything about absolute moments, because that will be a consequence of a growth assumption on the functions. So if we have 2 Lebesgue measurable functions, f and g, real valued on the real axis, neither one vanishing almost everywhere and with the same moments, if we assume that each function has this upper bound for its absolute value, some constant times e to the minus some positive constant times the absolute value of x, then the functions are the same almost everywhere. And if they are continuous, then they are the same everywhere. So when it comes to the growth condition here, in the exponential, you have the absolute value of x raised to the power 1. That is optimal. You cannot reduce the exponent to any fixed number less than 1. There will be a counterexample, which in fact comes from the classical literature, showing that such a reduction is not possible. Then if we have complex valued functions, of course, we could just define moments in the same way using integrals, then the moments would be complex numbers. And if we were to assume that the complex valued functions have the same moments, and if they satisfy the same growth condition, we get the same result. The functions are equal almost everywhere, or everywhere if they are continuous, just by the same argument. Applying the previous thing to the real and imaginary parts. So how would you prove the uniqueness result for real functions? The only thing you need to do is to prove the divergence of that certain series. So if we have this growth condition for, say, f, then you can estimate, well, you get twice the integral from 0 to infinity, and you get something that's essentially the gamma function. Of course, the most important thing for growth is the n factorial. And when you take roots, the most important thing is that there's something like n to the n. And you get the same thing for g. And if you just plug these estimates in here, you get the lower bound at some fixed constant, depending on a, of course, and this capital C, divided by n, and therefore the series diverges. And if you think about the divergence of the series, you see that something like constant over n is kind of close to optimal. You could put logarithms and such. Yeah, and you could, of course, therefore change this growth condition a bit if you allow for that. But it is very close to being optimal. So little fiddling around could be done. Well, this example shows that Karlemann's result would not apply, and that doesn't mean that there's a counterexample yet. The counterexample is something different, but Karlemann's result would not apply if we take e to the minus absolute value of x to the power b, where b is between 0 and 1. In this case, one can just calculate what these absolute moments are. You get something in terms of the gamma function, and the usual estimates for the gamma function tell you that the term here is comparable to n to the minus 1 over b. 1 over b is bigger than 1, and so you get the convergence series. So Karlemann's result wouldn't apply. That doesn't say it doesn't work, but a bit later, a counterexample shows it really doesn't work. And here we have the counterexample after a bit of explanation. Signed measures, all of whose moments vanish. So if we are supposed to have two signed measures that have the same moments, then their difference is a signed measure, all of whose moments vanish. And if we would like to have an example of that arising from some function f, then examples of such functions f have been known for a long time. So Stieltjes in 1894 gave this example, whose growth rate is roughly like e to the minus the square of log x. So it doesn't go to 0 quite as rapidly as e to the minus some power of x. But then in this monograph of Schohat and Tamarkin, there is another example. They tend to be very careful about attributing everything. They do not attribute this to anyone else. So I'm inclined to think that Schohat and Tamarkin came up with this example. So here you have e to essentially a power x to the alpha, where alpha is less than 1. Alpha is of a special kind, but since s could be an arbitrarily large positive integer, alpha can be as close to 1 as you like, and that shows that that exponent cannot be improved to be something strictly less than 1. So if you make use of this function that has 0 moments, we see that, for instance, if you take these two functions, whose difference has 0 moments, then they have all the same moments. So we have two non-negative functions there with the same moments, and therefore you could not have uniqueness there. So with this type of a growth rate, you can no longer have a unique result. Well, that was uniqueness. How about positivity? So now you just take one signed measure. So suppose we have a signed measure nu on R, not 0, not concentrated at the origin, with finite absolute moments. And so if we have this same thing, that the series of the absolute moments of index 2n raised to the minus 1 over 2n diverges, and if this necessary condition for moments is satisfied, then nu actually is a non-negative measure. The proof is quite simple as well.
Just the fire drill test.
Okay.
Actually,
Well, since that necessary condition for moments was satisfied, we know that there is some positive measure nu1 that has the same moments as nu. And so the uniqueness result tells us that nu is equal to nu1, therefore nu is non-negative if this series here diverges. So we just have to get some information on these sums of absolute measures. Now, S star 2n of nu1, since nu1 is non-negative, that's the same as the moment itself. The moment was assumed to be the same as the moment for nu, and the moment is always at less than or equal to the absolute moment. And therefore, you find this simple estimate here. The sum to the minus 2 over n is at least, well, there is 2 times the minus 1 over 2n, and then just this 1 absolute moment to minus 1 over 2n. So the assumption that the series here diverges then obviously implies that the series required for the application of the uniqueness theorem also diverges, and there we are. That's So similarly, you then get the criterion for the positivity of a function. So if we have a real valued living measurable function on R, not zero almost everywhere, if we now assume that there's a growth condition, the absolute value of f of x is at most c times e to the minus ax, absolute value of x. And if the necessary condition for the moments is satisfied, the conclusion is that f is non-negative almost everywhere, or if f is continuous, then non-negative everywhere. One might note that this type of a growth condition includes other possibilities that may not be obvious. Like if you had a polynomial times e to the minus a absolute value of x, that would satisfy this. You just have to take a new a that's a little bit smaller. So there can be other things that don't look like this, but still satisfy this type of a growth condition. And again, reason is that, as we already saw before with this growth condition, that series for the absolute moments diverges.
Is this sharp somehow, this exponential decay?
This is sharp in the sense that you couldn't make the exponent of the absolute value of x to be smaller. But of course, if you think about the divergence of the series, it doesn't have to be 1 over n. It could be 1 over n log n. You could calculate from that how much you could weaken this. So you could always weaken this slightly. So from a philosophical point of view, we now see how this works in very rough terms to understand what's going on. For the moments of a non-zero sign measure to all vanish, the measure in some sense has to be large. If two different sign measures have the same moments, then their difference must be large. But if both sign measures are small, then their difference cannot be large, and so in that case, they cannot have the same moments unless they actually were the same sign measure. So that's roughly the philosophy there. I think that the people like Kahneman must have understood this, but they never said it because they never studied systematically sign measures. There was always this assumption that every measure considered is a usual non-negative measure. So in that sense, one can understand how some of the classical weak, and as I said, if you look at e to the minus x squared, instead of the comparison function having to be non-negative, if it were at least minus e to the minus, say, a absolute value of x, you would get the same result, uniqueness there. Well, now polynomials don't have finite moments, but if p is a real polynomial, we can multiply it by a suitable function so that the product becomes so small that it satisfies the various growth conditions. Not only that it has finite moments, but it satisfies the conditions for the absolute moment so that that series diverges. There would, of course, be many possibilities there. We could, instead of using e to the minus x squared over 2 like here, we could use e to the minus absolute value of x, e to the minus positive constant times the absolute value of x. We could use e to the minus ax squared where a is positive. I made this choice just because numerically, when you calculate certain integrals, it kind of works out nicely in this way without extra factors. But one could do other things too. So the polynomial then, of course, is as long as this extra factor is non-negative, the polynomial is non-negative on the real axis if and only if this new function is non-negative on the real axis. Therefore, we can apply the previous results to this new function f. So if we write down the polynomial in this form, we can calculate the moments. You get all of these integrals where you now have x to the n and x to the j coming from the polynomial. And of course, these integrals vanish if the exponent j plus n is odd. And if the exponent j plus n is even, then you get something involving 5 and the double factorial of n plus j minus 1. I think it's customary to write down this type of things in terms of the double factorial when you have integers because it kind of looks nice. But something that will come up later is that, of course, as is well known, this double factorial is basically just a gamma function at a certain point. Very often it's half integer rather than an integer. Then there's something like pi and some power of 2, but those are unimportant factors. But this will come up later at some point. That this can be. So therefore, in these terms, if we use this ad hoc notation, sigma j is 0 when j is odd, and sigma j is j minus 1 double factorial if j is even, it follows that the polynomial is non-negative on R if and only if in all cases you have a matrix of any index, any dimension k plus 1 and any real numbers c0 to ck, these sums are non-negative. Well, I don't have any specific problem that would be a pre-existing problem that I could solve in this way. So this is just a theoretical abstract observation in this way. But this is an if and only if condition, so maybe of some theoretical interest. Well, then, of course, if we are dealing with these polynomials and then the polynomial is not identically 0, then all these, then the measures are not concentrated at finitely many points. And so in terms of determinants, all the determinants, of course, have to be positive for this to work. So if you try this in any particular case and start calculating these determinants of the matrices whose entries are these moments, if you find even one determinant that's negative, you are done. You see that it is not true that the polynomial would be non-negative everywhere on the real axis. So if you try to test this, then you can start calculating the determinants. And if this fails, it fails after a certain finite number of steps. But of course, there is no particular bound for how many steps you need to take. If you have a polynomial or its coefficients parameterized by one or more real parameters, if you are in the parameter space in a compact set K, such that everywhere on this compact set, the condition fails, in other words, it is not true that P is non-negative on the real axis, then you can find some positive integer depending on this compact set, so that for every parameter in the compact set, at least one of these determinants will be negative. I thought of giving a few numerical examples here. They might not be of any great interest, but I decided to take a simple case. Let's take the polynomial to be x minus a, where x is real. Then, of course, there is no real number a such that p would be non-negative on R. So these conditions are bound to fail, but in what manner do they fail? So I put some graphs here of these determinants. So whenever for a certain a, the determinant is negative, then we know that's not going to work. Just taking the first determinant, we see already that if a is positive, it fails. After that, it would be enough to consider just negative values for a. If you take the next determinant, you see that the condition fails for those negative numbers that are between some number there, like roughly -1 and 0. Now you can, at this point, you can forget about all of these. You see, by the way, that the first determinant would not be excluding many of the positive values that the first determinant excluded. And then you can continue in this fashion. So in terms of calculations, we can forget about these square root 2 pi factors. They are the same for everything, so they can be divided out. The first determinant was minus a. It excludes any a for which the determinant is negative, so it excludes positive values of a. Then the next determinant excludes also a between -1 and 0, and then it continues in this way, but the bit of thinking shows that no finite number of determinants can exclude all real a. So then we could do same things using different functions. We could use e to the minus the absolute value of x instead of e to the minus x squared over 2. There are some technical reasons related to just this polynomial and not universal that this choice eliminates values of a little bit faster. If we look at x squared minus a, well then of course this polynomial is greater than or equal to 0 on the real axis if and only if a is less than or equal to 0. So the criteria will be satisfied, but they will have to fail for every positive a. And so what happens here is that when you take the first determinant, certain positive values are excluded, but there are some values close to 0 where they are not yet excluded. And the pattern continues in this way. You get closer and closer to 0 by taking more determinants, but no finite number of determinants can exclude every positive a. Maybe we jump over the rest here. Now, if we then look at polynomials in several real variables, let's just look at 2 real variables, and that shows the principle of how this can be applied to deal with any number of variables. So if we have a polynomial in 2 real variables denoted by x and y, it would be something of this type where the aij are real numbers. So the idea is to first fix one of the variables, doesn't matter which one. For example, x, take x to be x naught. Then you have a polynomial in y. You would like this polynomial in y to be non-negative on the real axis. Okay, multiply by e to the minus y squared over 2, and then apply the previous results to this function of y. We find that f of y is non-negative on the real axis if and only if these expressions are always non-negative, where again these CP are arbitrary real variables. And the sigma notation is the same as before. Well, now we would like this to be true for every choice of the real number x naught. So we replace x naught by x, and we get another polynomial in x, which we want to be non-negative. This would be for every fixed choice of the integer k and these real numbers c naught, c1 up to ck. With that choice, it's a polynomial in x. So now we just multiply that polynomial of x by e to the minus x squared over 2 and apply the same system. And now we get a new system here. So any positive integers k and l, any real variables c naught to ck, d naught to dl, and all of these expressions should be non-negative. So what happens here is that, of course, we get more and more variables and an infinite number of conditions. If anything has been achieved, it is that all the new variables appear only quadratically, while in an arbitrary polynomial, the original variables can appear to any high power you care to name, depending on the polynomial. So you might think that maybe you gain something, you lose something, but you can also express these conditions in terms of determinants, and they are if and only if conditions. Now, if you take a polynomial with real coefficients in any real finite number of real variables, it's said to be a positive polynomial if it's always non-negative. And so in one variable, a polynomial is positive if and only if it can be written as a sum of squares of 2 polynomials. For 2 or more variables, this is no longer the case. But the solution to Hilbert's 17th problem states that such a polynomial can be expressed as a sum of squares of finitely many rational functions. And in fact, you can make a choice for the denominator. You can take it to be 1 plus sort of a square norm of the variables to some exponent, capital N, that may be very high, depending on what polynomial you are dealing with. There are very few examples of positive polynomials known that are not sums of squares of polynomials. And I've listed a couple of them over there. By the way, somehow positive polynomials, moments, and positive definite functions and matrices are all related. If you have a book on about any one of these topics, it typically has at least one chapter on the others. So I thought of mentioning that one can use this system to construct examples of positive polynomials. First, you take a polynomial of one variable, which is certainly non-negative. So if you then calculate the moment of the polynomial times e to the minus x squared over 2 and take these determinants, they are guaranteed to be positive. But now these determinants, of course, x has disappeared. These determinants are polynomials in the parameters you put here, like the zeros and such of the polynomial you are dealing with. So you get positive polynomials in these new variables, the parameters. So I calculated some examples here. These quickly become extremely long expressions. But my impression is that unfortunately, these look like sums of squares of polynomials. So I doubt that one can get new counterexamples that way. But it might be, it certainly is an open problem to prove that all polynomials you get in this way indeed are sums of squares of polynomials, if anybody is interested. Well, then there are problems where it has been shown that something is true if and only if certain polynomials related to it are non-negative on the real axis. So Polya proved that if you start with the real polynomial p of degree 2, then p has only real zeros if and only if every one of these n-1 polynomials is non-negative on R. And so if you then take all of these polynomials and multiply by e to the minus x squared over 2, you could express the condition that the polynomial is non-negative in terms of the moments. I didn't want to write that down explicitly because it becomes very lengthy, and I have other things still to say as well. I will not end early. Okay, so this is the obvious thing, that a consideration of these moments leads to conditions that are quadratic in the coefficients of the original polynomial. That's because these new polynomials are quadratic with respect to the original. Another result of Polya is that if you take a real entire function of genus 0 or 1, not of the form e to the a z times a polynomial, then all the zeros of the entire function are real if and only if for all n greater than or equal to 1 and for all real x, these polynomials that again have quadratic dependence on the coefficients of f are positive on the real axis. The polynomials fn are determined in this way. So it doesn't amount to just taking the coefficients from the original f, but modifying them a little bit. And these conditions on these polynomials fn could also be then tested by looking at moments. I don't know how to prove that any specific real entire function of this type would have only real zeros using this method, but I guess later on somebody might be able to do something about some interesting case. Okay, for the last few slides, I really want to talk about two things. One is this question here, and the other thing is a kind of special case related to differential inequalities for the gamma function. So why did I think about the gamma function at all? To explain that, let's go back quite a bit here, where we encountered a double factorial for the first time. And I mentioned that the double factorial, apart from some unimportant multiplicative factors, is really just the gamma function evaluated at a certain positive number, which very often is a positive integer plus 1/2. So that led me to think about the gamma function. So after all of that explanation, let's look at the question first. Now, we saw in that theorem that the sufficient condition for the uniqueness of sign measures was that this particular series diverges. And it was enough for everything that followed, no problem. We got everything out of this. But as an intellectual question, one could ask whether this condition could be replaced by something where the sign measures are not combined in this way, but each of these two individual series diverges. So if one wanted to prove it, one would have to ask what kind of facts or properties of the absolute moments of sign measures would need to be used to prove such a thing. Well, it's easy to see it's not enough to use the fact that these absolute moments are positive numbers. Let me explain that very briefly because it's real simple. And for that purpose, we can forget about taking these roots. If you think about the bit, you see the issue really is the same whether or not you have these roots. So suppose that we have two series of positive numbers so that every term is of the form 1 over a positive number. Suppose that for one of the series, the denominators alternate between n and n squared. Then the series diverge. Suppose that for the other series, the denominators also alternate between n and n squared, but the other way, so that series also diverges. If we now form a new series by adding the denominators together, then every denominator is n plus n squared, and the new series converges. So that was certainly not enough. Other properties of these absolute moments. Well, already Carleman observed, and it follows immediately from Hölder's inequality, that log of s star to n is a convex function of n. But this doesn't seem to be enough either. If I have time, I'll draw a little picture explaining that, but that's not enough either. So therefore, we should look for further properties of these numbers s star. Now, since there's going to be some relationship to polygamma functions, let me recall how they are defined. Everything on this slide was, as far as I know, was known to Gauss. So the definition is that you take the mth derivative of gamma prime over gamma, or alternatively, you could say you take derivatives of log gamma. And there is this integral representation, which, I don't know if you've seen it before, but it really is not too hard to derive, that Cm is minus 1 to the m plus 1 times something obviously positive, namely this integral. So therefore, it immediately follows that minus 1 to the m times this function Cm is positive for all positive x. So if you now start differentiating and calculate these things and get rid of denominators by multiplying by powers of gamma, you see that certain differential polynomials of gamma are positive on the positive real axis. The first one of them, of course, tells you the well-known property that log of gamma is a convex function of x. Then the second one might be less well-known. One has to do a bit of effort to compute what this is equal to. By a differential polynomial, I mean a polynomial in a function and it's some of its first few derivatives, and in this case, constant coefficients. In value distribution, there might be coefficients that are functions, but here just constant coefficients. So since I will be using this more complicated one as an example in many other comments, well, here it is. So matrices or determinants that have the property that when you move along skew diagonals, that means these diagonals sort of in the other way around, and the ordinary diagonals, that they are constant along the skew diagonals, they are called Hankel matrices. The determinants are Hankel determinants. Well, you can use software like Mathematica to calculate these determinants and ask Mathematica to factor them for you. For a general one, you get nothing, just a one factor. But now if we are in a situation where every second skew diagonal is 0, then you start getting factorizations. And so just to show that this makes sense, if we start with the sign measure, A is a measure, say, a Borel subset of the real axis, you can define a new non-negative symmetric measure nu1. All the odd moments are 0, and the even moments are the absolute moments for the original sign measure. And so the positive definite matrices you get would be exactly like these. So many other factors appear for larger determinants. For instance, the analogous 7×7 determinant would have the factor that I've given here. I will return to this particular factor later, just as to give an example. But you see that you start getting factors They just get longer and longer, but very often you have two factors and one is considerably shorter than the other one. The product is positive. Therefore, both factors are positive or both negative. The computer gives you these factors in a random fashion, so you have to figure out how to put the signs, but then you find out what the positive factors are. But then it's going to be systematically positive. By the way, of course, these factorizations are algebraic facts that would be valid even if you were to use complex numbers for S0, S2, and so on. So there would be nothing about positivity there. But if they arise from these absolute moments, then you have these positivity properties. So now how to get to the gamma function? So now there's an idea. There was the idea of how to prove that certain matrices are positive definite using moments. We can expand that idea and put here something that are not exactly the moments, but something similar. So we can choose a positive real number h, a real number a that's bigger than -1. So a plus 1 is an arbitrary positive real number. And then, of course, an integral like this is positive, and that can be written in this form where we have a matrix with elements Tij. The odd elements are Ti plus j, the odd Tn's are 0, and the even ones are values of the gamma function. So if you now take this thing that's going to be positive, divide by 4h squared, let h tend to 0, then you get exactly that differential inequality for gamma function that expresses the fact that log gamma is convex. And this is then valid for every positive real number because n plus 1 can be any positive real number. So suppose that we take this next thing that was awfully complicated and do the same thing there, take the limit. Well, then you get this next polygamma thing. So I suspect that if you calculate these things further, this is a very recent idea, so I haven't calculated anything systematically, but I suspect that when you get more and more of these factors, you get properties of the gamma function that a certain differential inequality for gamma function has to hold. There's probably some limit to how many differential inequalities for the gamma function can satisfy, and I suspect that you just get these polygamma inequalities. Well, you could then still ask something here. You get these factors. And if you take something simple like S0, S4 minus S2 squared, and there are many other similar ones, we already know that these have to be positive because log S2n or log S2n star is a convex function of n. The positivity merely expresses this fact. If we were to take this more abstract point of view that there are these factors that we know that, well, they are positive or negative, how would you know that this particular one is positive rather than negative, especially if we take something more complicated? Well, we can do it in the following way. So you write this thing twice. So in the second line, it's clearer because I had more space. The fourth moment times the 0th moment minus the square of the second moment. So it is the same thing on this first line, but since I had less space, I had to write it a bit differently. So you add it to it and you kind of symmetrize it because here you have nothing and y, here you have x and nothing. So if you then see what happens here, you get the double integral with respect to d nu x, d nu y with this integrand, and the integrand is quite obviously always non-negative. So as long as nu is not a degenerate, you get the positive number. So what about this more complicated thing? How could we prove that this more complicated thing here is positive? Well, now you always have a product of 3 moments. You get always a triple integral using real variables like x, y, and z. You symmetrize like here, and so you find that the integrand is a very long and complicated polynomial in x, y, and z. But if you ask software to simplify this polynomial for you, this is what you get.
It is what?
If you ask software to simplify that polynomial for you, then that is what you get. Obviously something non-negative. So in this way, you can see that certain expressions really are positive. Furthermore, you have here a way of, and you see a certain pattern of generating more and more polynomials in the moments or absolute moments that are guaranteed to be positive, each of them would correspond to a valid differential inequality for the gamma function. Now, if you take any finite number of differential inequalities for the gamma function, if you take a linear combination with positive coefficients, you get another differential inequality that's valid. You could ask, what are the minimal ones that cannot be decomposed in a non-trivial fashion? I don't know if anybody ever asked that question. And so, of course, I don't have the answer. If one had to make a guess, I would guess maybe the polygamma inequalities would be the minimal ones. That's something one could ask. Anyway, so here is a rather compelling way of seeing why these simpler quantities rather than the full determinants will be positive. So I wanted to say that this gives more properties for the function log S2n or S star 2n other than just convexity. It will force stricter bounds between where these two functions have to be. And the idea is that if you wanted to prove that the divergence of each of the two series implies the divergence of the third series, that's roughly what you need. The two functions would have to be close enough to each other, and there are infinitely many possibilities here that one could keep adding. I'm sort of hoping after finitely many cases, one would be able to prove that statement. Well, with flowers from our own yard, happy birthday to Alex.